Pluto is a distant and covert, more humble planet that was once a piece of our close-by planetary framework. However, ongoing momentous statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking exposure. They recommended that this frigid world is on a potential impact course with Neptune. Yet, how could this function, and what might be the consequences of such a fascinating astronomical inconsistency? Or is there something else to this looming, unending calamity? Join us as we inspect the likely results of a Pluto-Neptune crash. Pluto, a former planet that was subsequently renamed as a dwarf planet, remains a subject of interest and focus in the vast universe, as shown by ongoing research from leading specialists. Pluto's orbit is dangerously close to Neptune's, and astrophysicists Neil deGrasse Tyson and Michio Kaku have raised the alarm about a potential risky influence between these two planets, which could pose a significant risk to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our nearby planetary system. It takes an astonishing 248 years to complete a single orbit, and since its discovery in 1930, it hasn't even finished one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its unusually elliptical shape, meandering greatly from the nearly round orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, which is tilted at 17 degrees to the ecliptic plane. The way Pluto follows its path is far more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital arrangement. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the planetary system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to figure out its peculiar path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and elongated shape. The mystery grew with the realization that Pluto's orbit crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they started and how they pull on one another. For Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex way. The terms non-synchronous libration, orbital precession, and VZK oscillation are important in this puzzle. According to astrophysicists, what keeps all planets in their orbits is non-synchronous libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned around 90 degrees away from Neptune. This spatial separation is crucial in keeping their orbits from merging. Orbital precession, on the other hand, refers to the upward movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated far above their orbital plane, providing an additional layer of protection from potential collisions. Another critical factor is the VZK oscillation, named after three scientists who studied how objects move in space. It involves the way three space objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This gravitational force affects how they move. For Pluto, the VZK oscillation explains why its orbit near the Sun is so unpredictable. Despite Pluto's path seeming unusual, this oscillation helps keep it moving smoothly over long stretches. The VZK oscillation shows that, although things in space may seem chaotic and erratic, certain patterns and rules keep everything in balance. These factors help keep Pluto's orbit stable, ensuring that it doesn't collide with Neptune or drift off course. The three-body problem is essential in understanding how these orbits change because of the way space objects pull on each other. Studying this helps us learn more about Pluto, our nearby planetary system, and even distant galaxies and their stars. Mathematical simulations in the late 1980s revealed that, despite these stabilizing factors, Pluto's orbit is actually unstable. Minor deviations in initial conditions can lead to significant differences over millennia. However, these irregularities in Pluto's orbit have been found to maintain stability over extraordinarily long timescales. Observing this disruption has been crucial, as later computational assessments have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune is not the only planet at play. Jupiter's gravity also plays a massive role in stabilizing Pluto's orbit, and Saturn contributes as well. These studies show that Jupiter's immense gravity is strong enough to ensure that Pluto remains on a consistent path for a long time. So perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These irregularities are crucial in keeping everything under control and maintaining stability in space. Without these factors, the solar system as we know it would be a much more chaotic place. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto, especially with discussions about it potentially colliding with Neptune in the future, understanding its orbit is vital. This gives a clearer picture of the dynamic nature of the solar system. The case of Pluto shows how even the most seemingly unstable orbits can reach a state of stability through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of constant observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the strange nature of celestial bodies. Moreover, Pluto's orbit is a perfect example of the volatility of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions. This is clearly illustrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can drastically alter its long-term orbit. Using virtual simulations has been immensely helpful for scientists in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects, like Neptune, pull on one another. By tweaking small details in the simulations, space analysts can see how even minor changes can dramatically affect where Pluto ends. In the late 1980s, these simulations showed something intriguing about Pluto's orbit. Despite having features like non-synchronous libration and orbital precession to keep it stable, Pluto's orbit can still be erratic and unpredictable if you start with even a small difference in where Pluto is or how fast it's moving. Its orbit could end up looking completely different after just a few years. However, even with this turmoil, Pluto's orbit remains stable over extremely long stretches, like billions of years. This essentially means that Pluto's journey around the Sun has a kind of order to it, even though it seems chaotic at first. Predicting celestial events, especially when they involve erratic orbits like Pluto's, is a huge challenge. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical models provide great tools for understanding and predicting the future motions of celestial bodies, they also highlight the limitations of our predictive abilities. These models rely heavily on the accuracy of initial conditions, and any small error or distortion can lead to vastly different outcomes, making precise forecasts a daunting task. Moreover, the turbulent nature of planetary orbits like Pluto's reminds us of the ever-changing, dynamic nature of the universe. While we've made tremendous strides in understanding space, Pluto's case reminds us of how much our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly influence the stability and trajectory of other bodies within the system. So why are leading astrophysicists recently raising concerns about a potential collision between Pluto and Neptune, despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in advancing cosmology, offers a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful views on the evolving nature of celestial mechanics and the public's interest in the overlooked realms of space. Tyson's stance on Pluto's renaming is based on the ever-expanding knowledge of our solar system. He sees the renaming not as a diminishment, but as a significant change in alignment with our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of constant learning and adaptation. He views the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The fascination with these questions keeps space exploration so captivating. However, despite Tyson's confidence, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the future of Pluto's orbit suggest that there may still be some mysteries left to uncover. Will Pluto crash into Neptune? Or is this just another moment of confusion in the ever-changing universe of space? Only time and further research will tell. For now, we are left with a deeper curiosity about how little we still know about our own solar system. We continue to study these celestial phenomena with the hope of uncovering more of the mysteries that lie beyond. The possibility of a Pluto-Neptune collision raises another question about the intricate and captivating universe in which we exist. The potential for a crash between Pluto and Neptune raises fascinating issues about the dynamics of the solar system, as it challenges conventional understandings of planetary stability. The idea that two celestial bodies with such vastly different properties could collide is both disturbing and intriguing, particularly considering the current relative strength of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be enormous for our understanding of gravitational interactions and the evolution of the solar system. To understand the dynamics of a potential collision, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains various elements and compounds believed to exist in a frozen state due to the supercold temperatures of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere made primarily of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is primarily composed of hydrogen, helium, and other lighter elements with a deep, thick atmosphere. A collision between such disparate bodies would radically affect their structure and behavior, potentially creating an event visible across vast distances. What makes this speculative impact particularly striking is the effect of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only variable at play. The presence of Jupiter, the largest planet in the solar system, is another key factor. Jupiter's immense mass, powerful gravitational field, and gravitational pull provide a stabilizing influence on Pluto's orbit, preventing it from wandering too far into Neptune's domain. Furthermore, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making it unlikely that a catastrophic event will occur between Pluto and Neptune. The study of Pluto's orbit, as well as its potential interaction with Neptune, highlights the complexity of planetary dynamics in our solar system. The primary concern among astrophysicists like Neil deGrasse Tyson and Michio Kaku is not just the possibility of a potential impact, but how such an event could be influenced by factors beyond Pluto and Neptune themselves. The gravitational interaction between these two distant planets is heavily influenced by interactions with the larger, more massive bodies in our solar system, especially Jupiter. Jupiter's gravitational field, with its enormous mass, acts as a safeguard, applying enough force to prevent Pluto from wandering too far into Neptune's orbit. Without Jupiter's stabilizing influence, Pluto could potentially drift into more erratic paths, increasing the chances of a collision with Neptune. Saturn's role, while often overshadowed by Jupiter's gravitational strength, still provides subtle adjustments that help maintain the balance of the outer solar system. These two giants, along with Neptune, work together to ensure that Pluto's orbit remains predictable despite its eccentricities. Without these forces at play, the outer regions of the solar system could become much more chaotic. This delicate balancing act of gravitational forces across different planets also underscores the broader implications of planetary evolution over billions of years. These forces have shaped not only the orbits of smaller bodies like Pluto, but have also impacted the overall architecture of the entire solar system. For example, the movement of gas giants like Jupiter and Saturn over cosmic time is believed to have had a significant impact on the orbits of transneptunian objects like Pluto.